We continue to look inside the formerly black box. We studied Gaussian elimination, which is used in the modules solver and independence when working over GF2, and we'll next study the methods used in these same modules when working over the real numbers. There's a burning house located at coordinates 2, 4. Now, fortunately, there's a street that runs close to the house, but is it close enough? The street goes through the origin and through the point 6, 2. And the fire engine has a hose 3.5 units long. So we can navigate the fire engine to the point on the road closest to the house. But if we do that, will the distance from the fire engine to the house be close enough for the hose? Well, there are two questions that we're looking at. What point along the street is closest to the house, and how far is it? And to answer that, we first have to say what we mean by closest. The distance between 2 points P and B is the length of the difference, P minus B. We first have to define the length of a vector. Instead of using the term length, we use the term norm. Now, the norm of the vector is written with these double vertical bars. A norm should satisfy certain properties. The norm of a vector should be a non-negative real number. That's part of what we mean by length. The norm of a vector should be 0 if and only if the vector is the 0 vector. And the norm should scale. That is, if you scale a vector by an amount alpha, then that should change the vector itself by the absolute value of alpha. And finally, norm should satisfy something called the triangle inequality. Well, one way to define a norm for vectors is to first define an operation on vectors called inner product, which is written this way: the inner product of u with v. Now, inner product itself has to satisfy certain axioms, and we're going to get to those soon. One thing to note, though, is there's no way to define an inner product for the field GF2. So we're going to have to say goodbye to GF2. Now, for the real and complex numbers, we can define an inner product. In fact, there is some flexibility in how we define the inner product, and that flexibility is very useful in applications. Once we've defined an inner product, we get a norm. The norm of a vector is the square root of the inner product of the vector with itself. For simplicity, we'll focus on the field of real numbers, and we'll use the most natural and convenient definition of inner product. And that definition will lead to the norm being what you think of as the length of a vector. That is, the geometric length of its arrow. So for vectors over the reals, we'll define the inner product of u and v to be just the dot product of u and v. The inner product has several properties. It's linear in the first argument, which means the inner product of u plus v with w is the inner product of u with w plus the inner product of v with w. It's symmetric. That is, the inner product of u with v is the same as the inner product of v with u. And it satisfies homogeneity, which means the inner product of alpha u with v equals alpha times the inner product of u with v. And it's easy to prove these properties when we define our inner product to just be dot product. All right, so we've defined inner product to be dot product, and we've defined the norm of a vector to be the square root of the inner product of a vector with itself. Do we thereby get the norm properties? Does our norm behave like a distance? Let's write a vector v in terms of its entries, v1 through vn. Then the norm of that vector v is just the square root of the sum of the squares of the entries. Now, the sum of squares is a non-negative real number. Then we take the square root, we still get a non-negative real number. So, in fact, the norm of v is a non-negative real number. That's the first property. Now, if any entry of the vector v is non-zero, then this sum of squares is bigger than 0. So the norm is non-zero in that case. So that shows that the norm satisfies the second property. I'll go through the proof of the third property. Let's look at the norm squared of alpha times v. That's the inner product of alpha times v with alpha times v. We can factor out one of those alphas, so we get alpha times the inner product of v with alpha v. We factor out the other one, so we get alpha times the inner product of v with v. And that's just alpha squared times the norm squared of v. So that shows that the third property is satisfied. And we're going to skip the proof of the fourth property. Here's an example. We have a 2 vector, u1, u2. What's the norm of that vector? Well, recall the Pythagorean theorem. For a right triangle with sides a, b, and c, where c is the length of the hypotenuse, a squared plus b squared equals c squared. We can use this equation to calculate the length of this vector u. The squared length of u equals the sum of the base squared and the height squared. So at least in the case of 2 vectors, this notion of length agrees with the one you're familiar with.